Okay, 4-3 is the section that we're looking at here today. And in this section, our topic is graphing logarithmic functions. All right, now in the first two sections, we looked at exponential functions. So now beginning in 4-3, we're looking at what is known as logarithmic functions. And again, logarithmic functions were a topic you did cover in Algebra 2. So once again, shouldn't be completely new to you. However, this section starts off with the idea, right, that the logarithmic function is the inverse, okay, of the exponential function. So logarithmic functions are inverses of exponential functions, right? And it just kind of goes through a little bit of the notation right here. And also gives you how to read it. Okay, and so this is telling us that if f of x equals b to the x power, now there's some conditions here. B has to be greater than 0, because if b is negative and you raise it to an even power, negative and negative, even makes a positive, but if you raise it to an odd power, you're left with a negative result, and so it's bouncing positive, negative, and it wouldn't be like a continuous function, right? So that's why it's got to be greater than 0. And b also cannot be equal to 1. So your base cannot be 1, because what happens then? Well, if my base is 1, it doesn't matter what power I raise it to. It's still always going to be 1, and then it's just in essence a constant function. So it wouldn't really be exponential anymore in that case. All right? So again, if you've got the exponential function, then the inverse function is equal to log base b of x. So these two functions are inverses of each other. Okay? And when you graph these two functions, notice that they're reflections through the line y equals x, which is the graphic representation of two functions that are inverses, right? So again, exponential function and logarithmic functions, they are inverse functions. Much like the way that squared and square root are inverse functions, right? So they one undoes the other. As a matter of fact, that's the illustration I want to give to you right now. Okay? So suppose I have this example. F of x equals to 5 to the x power. 5 to the x power. There's my function, right? Okay? And so let's just evaluate this for f of 2. So I'm going to put 2 in for x. That's 5 squared. Okay? Well, what does 5 squared equal to? 25. All right? And so let's take a look at the inverse of this function. So the inverse of this function would be log base 5 of x. That would be the inverse of this function. Log base 5 of x. Okay? All right, so these are the two inverses. If we want to verify that, we could plug in f of 2. All right? So that would be log base 5 of, whoops, sorry, I don't want to put in 2. Remember, if they're inverses, whatever you get out of the first one, you should put into the inverse, and then it should take you back to what you put in first. So I actually don't want to put in 2 if I'm trying to show that it's the inverse. I want to put in what I got out the first time, which is 25. All right. Okay, so if I wanted to show that this is indeed the inverse of this function, when I put in 25, which is what I got out of the last one, I should get 2, which is what I started with in the inverse. All right, so I want log base 5 of 25, and I want to see what that equals. Okay, so remember, log base 5 of 25, remember that what that means is, that means 5 to what power, this is now my blank, 5 to what power gives me 25? Well, we know 5 to the second power gives me 25. 5 squared equals to 25. Okay? So again, when you write it in log form, this number is your base, this number is your exponent, and this is the number you get when you take this base to this exponent. Okay? So that's what log form is. It's just rearranging the parts from the exponential function. That's all it is. All right? So I know when you first see logarithmic functions and start looking at them, it looks strange, but just remember, this is the base, this is the power, and this number is what you get when you raise this base to this power. All right? And again, we can verify that this is indeed the inverse. When I put in 2 to this function, I got 25. When I put 25 into the inverse, I got 2. So it went backwards, back to what we started with. So it is indeed the inverse. All right? So now we come relating a segment here where it's relating the logarithmic and the exponential forms. Okay? And so this logarithmic form, okay, then this is the logarithmic form if and only if this is the correct exponential form. So this really explicitly kind of shows you how things are being rearranged from one to the other. Like, for example, in the specific example I use, this would be log base 5 of 25 equals to 2. Why? Because 5 squared equals 25. This is your base in log form. This is your base. This is your exponent. This is what you get when you raise this base to this exponent. 5 squared is 25. Well, in exponential form, then, that would just be it. 5 squared equals to 25. All right? So sometimes it's easier to see how it's rearranged when you plug in regular numbers to see how this thing is working instead of just x's and y's. So you can see that my base raised to the y power equals x. Then it's log base b of x equals to the exponent. So remember, in logarithmic form, this is your exponent right here. Okay? So like I say, you just have to get used to the way that the logarithmic format is rearranged. And once you get used to that, it's no problem. Okay? All right. So just like we have been in some of the other units, and just like we did with the exponential functions, we're going to look at some of the characteristics of the logarithmic function. So we have the logarithmic parent function here. And so we've got it graphed. And we're going to look at some of the characteristics. Okay, so we have the graph here. The domain of this parent function, okay, is from 0 to positive infinity. Okay, it doesn't go negative, right? The range is from negative infinity to positive infinity. Okay, we have an intercept at 1, 0. That is the x-intercept. There is no y-intercept. Notice that's an asymptote. Okay, let's see. And it's increasing on this interval from 0 to positive infinity. That's your interval over which it's increasing. Okay, the y-axis is a vertical asymptote. All right, and so the function itself approaches negative infinity as x approaches 0 from the right. Okay, so we can verify that. It's continuous. It's not broken anywhere. No holes in the graph or jumps or anything like that. And it's a reflection of the graph of f of x equals a to the x power through the line y equals x. Why? Because it's the inverse of this exponential function. So these are the characteristics kind of that we're going to be looking at some of the various logarithmic functions. And so really that's all we're doing in this section is looking at the characteristics. We're not calculating anything with log or anything like that yet. But that part is going to be coming in some of the subsequent sections. All right. But for this particular section, all we're going to be doing is we're going to be taking a function, right? And so here's my function, y equals log base 2 of x minus 1. And these are the characteristics that I want to find. And as usual, just like we have been, we're going to graph this function and use the graph to determine these characteristics. So once again, I have my Desmos app on my phone. We'll pull it up. Clear the old ones off, and let's go ahead and plug in the function that we have here, which is going to be log. If I press this function key, I should be able to find log here somewhere. There it is. It's under miscellaneous. Okay, so plug in log, and we want log base 2. Let's see. It can give me base 2. It should be able to. You know what? I'm going to have to pause this for a minute, and because I don't remember where to get it from. Hold on a second. I'm going to pause it. All right, I had to pause for a minute to figure out how to input it into this Desmos. I haven't done log in Desmos calculator for a while, and I've forgotten how to do it. And so what you'll do when you go to the functions, there's another log right next to it that's asking for the base, right? And so that would be this one right here that we need to pick, not this one. By the way, if there's no base specified in log, it's understood to automatically be base 10, by the way. But we want to have base 2 of this one. And so I'm going to go ahead and put this here. And so now it's asking me for the correct base. So log base 2, so I can put my 2 in there. And then now we can put in the x minus 1, and we close it off. Okay, now we have the correct graph. All right, so on the graph now we can start looking for these different characteristics. Right? And so one thing that we will notice and what we'll get into in the next section is how the graph is moved in the transformations. And so remember, if I'm subtracting 1 directly from the x, that typically means that we're going to move 1 to the right. And that is the case here. And so what that allows me to understand is that the graph is shifted over. And so what that means is when I'm looking for the domain, I know that this time the domain is actually going to start at 1 and then go up to positive infinity. Okay. If I needed to verify that, I could just by probably adding a table if I needed to. Let's see. So if I go here and we add a table to it. All right. Negatives, by the way, undefined. And at 1, it's even undefined. So we see it doesn't start becoming defined until we get to 0. Now if I put 1.1 in there, yes, we get a value. All right. So again, starting at 1, not including 1, because at 1 it's actually undefined. All right. And so trying to get back to my function. There we go. Turn my table. Oh, I lost everything. That wasn't good. Let's put this back on here. So I'm going to graph it again. And it's x minus 1. All right. Okay, so again, my domain actually starts at 1 to positive infinity. The range now, there is no boundaries or limitations on the range. It's negative infinity to positive infinity. All right, so we're good there on domain and range. Find the intercepts. There's only an x-intercept right here at 2. You can write it as an ordered pair, or you could write it like this, x-intercept, and then list the value at 2. Either one would be acceptable. You could write it like that, or you could put the point 2, 0 as your intercept. Either way, sometimes you will see it on as written as both ways, depending on what resource or what assignment you're looking at. Okay, find the asymptotes. There is one. Okay, right here at a vertical asymptote at x equals to 1. All right, so that's the limit that the function approaches there. All right, now we want to describe the end behavior. So we want to describe the behavior now on each end. Okay, and so we'll use our limit notation in order to do that. And so we want to start with the left-hand side. And so the limit, okay, on the left-hand side of this graph, as x approaches 1, all right, so as x approaches 1, okay, the limit of the function, all right, is going to be y equals to negative infinity. All right, so it's decreasing without bound as x approaches 1. So again, the limit of y as x approaches 1 is negative infinity. Okay, so that is the left-hand end behavior. Let's go for the right-hand end behavior, which will be the limit as x approaches positive infinity, because there's no boundary on this side of the function. And by the way, if you're looking to see what your x needs to approach to describe your end behavior, look at the domains, right? This is what x approaches for your left end behavior. This is what x should approach for your right hand end behavior. All right, so as x approaches infinity, the function itself continues to grow bigger and bigger without boundary, as we can see there. And so that's going to approach infinity. All right? And so you might be asking, well, Coach, how do we know it's not a horizontal asymptote here? If you wanted to add a table and put some big values in, you could. like when we go to 100, still get a value, still get a value, still get a value. You see what I mean? Every time I add a 0, it's still just approaching something bigger and bigger. There's no boundary, all right? So you can, you can't see that on the calculator, but I just kept adding zeros to this and the number just kept growing. Perhaps I should show that again since we couldn't see it very well. Okay, so at 10, 100, 1,000, 10,000, 100,000, right, a million. It just keeps going up. It's not approaching any number. It's just steadily increasing. Okay, so infinity is what the function approaches there. All right, let me see here. And give the intervals for increasing or decreasing. And so the function is increasing. It doesn't have any intervals where it's decreasing, so it's increasing. And it's increasing over the interval of the entire domain, which is 1 to infinity. All right? So there you go. So that's how we can describe all 5 of these characteristics for this particular function. Okay, we have another one that we want to look at. So I'm going to clear this graph off, and let's start with a new one. Let's see. Okay, so my next function is going to be 2 minus, go here to functions, miscellaneous functions, log with the base is what we want, base 2. And inside my parentheses, I will just put an x. All right, so here's my function. Okay, so once again, the same characteristics is what we are trying to find here. So we'll start with domain and range. So we got domain there. And the domain is going to be starting here at 0 because there's nothing here that's moving it left and right. Just the movement 2 up is all that's being shifted here. And so really our domain is going to start with 0. Okay, and from there it goes up to positive infinity, no bound. There's the domain. Checking the range now. All right. And so for my range, okay, we are looking at a range value that actually, remember there's no lower bound because it continues on. If you wanted to use the table to verify that, you could. So my range is going to be from negative infinity and, of course, increases without bound to positive infinity. There's my range. Okay. What about the intercepts? There is an x-intercept. I will click there to find that it's 4. And so I can write it like this, x-intercept 4. Or writing the ordered pair, as we said earlier, would be fine. All right, the asymptotes, it does have a vertical asymptote, and we know that's at x equals 0. Right, there's my vertical asymptote. Describing now the end behavior. And so, again, I can go to my domain to see what the x values on the left and right end should be. And so for my first one, I want to know the limit of the function as x approaches 0. Okay, as x approaches 0. Okay. And so as the x approaches 0, and by the way, I don't have to list from the left or from the right on this one because it only approaches 0 from the right. The function does not approach 0 from the left. All right, so when it's approaching from both sides, that's when you have to indicate from the left and from the right by putting a plus and a minus there. So just wanted to make sure I clear that up. Okay, but if it's only approaching from one side, you don't have to indicate because it's only going from one side. Okay. All right, so the limit of the function as x approaches 0. All right, so let's see what that is. So as x approaches 0, now what's happening to the function? Increasing without bound. Infinity is what is it approaching there. That's the left hand in behavior. Let's go now to the right hand in behavior. It's going to be the limit of the function as x now approaches. All right, so on the right hand there's no bound, right? We knew that from the domain. So on the right hand, we want to see what the function is doing as x approaches positive infinity, right? And so as x approaches positive infinity, what's happening to the function itself? It's continuing to decrease without bound, so that means it will go to negative infinity, all right? So that is your end behavior. What about the intervals for increasing or decreasing? This particular function is decreasing over the entire domain. Okay, decreasing, and that's going to be from 0 to infinity. All right? So there you go. Quiz is waiting for you there, and we'll be back soon with the next